So the last section from the Unit 2 Part 1 new content is actually from Unit 6 in our textbook. Our textbook uses a what's called late transcendentals approach to calculus. That just means that transcendental functions, which are trig functions, inverse trig functions, exponential, logarithmic, those kinds of things, are not covered until after you've already learned derivatives and integrals, and then it uses integrals to prove some of these derivatives and such. Okay, you don't need to worry about that, but basically we're rearranging, and I'm moving this up to Unit 2 because the AP curriculum is early transcendentals approach, meaning I want you to be able to see this before Chapter 6, and so we are covering that now. And so I'm going to start by going through the definition of the derivative to find the derivative of natural log, just so that we can prove this. Just like with the proof of sine or the other trig functions or the product or quotient rules, it's not something that you will have to be able to reproduce on your own. I'm not going to ask you to prove it on a quiz or a test, but it is good to know where things are coming from. So I'm going to start by using the definition that we got in 2.1 for the derivative to evaluate or to develop a formula for the derivative of the natural log of x. And then real quick before I do that, there are some review materials posted. I posted just a summary of everything you need to know about logs and exponentials as a PDF in the Unit 2 folder under the purple extra practice and keys folder, okay? And then also I created an assignment in Delta Math that is optional, but it's a good idea for you to look through and make sure you remember, like, properties. What do functions look like? How do we solve? How do we rewrite, convert between exponential and log form? So anyway, take a look at all that stuff and make sure that you are comfortable with logs. For 6.1 here, we're not going to do too much other than just the natural log, which is log base e, but we are going to have to use more log properties than you might remember. Okay, so using the definition, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, we're going to start with this. So I'm going to write this as the derivative of natural log x is equal to, the limit as h approaches 0 of, and so then f of x plus h is going to be natural log of x plus h minus, and then f of x is natural log x all over h, okay? And now we're going to start with log properties right off the bat. If we have subtraction of two logs with the same base, which both of these are base e, we can combine them with division. We can combine them as a quotient. So this becomes the limit as h approaches 0 of the natural log of x plus h all over x. So I'm doing x plus h over x, and then all of that is still over h. Okay, and then I'm going to manipulate this, move some things around a little bit. First thing I want to do is I'm going to take this h that's in the denominator and just write it as 1 over h in front of the expression, okay? So, and I'll go ahead and do this in two steps. So limit as h approaches 0 of 1 over h times the natural log of, and then using a little bit of algebra with this fraction here, I'm going to split that into two fractions and write this as 1, because x over x is 1, so 1 plus h over x. Okay? Now, for my next step, I'm going to switch colors so I can write what I'm doing here. I'm going to multiply this whole expression by x over x, and if I multiply by x over x, I'm not changing the value, okay, but where I put the x's is going to help me evaluate this, okay? So I'm going to write this first as the limit as h approaches 0 of, and I'm multiplying by x over x, so I'm going to write this as 1 over x times x over h, and then I still have the natural log of 1 plus h over x. Okay, so I've multiplied by x in the numerator and denominator, but for the denominator, I'm just keeping this 1 over x in front, and then I have an x over h. So I'm putting the x in the numerator on top of this 1 over h. Okay, now the reason I'm doing this, okay, is for my next step, because the limit of this expression is, or the variable of this limit expression is an h, then x is operating essentially as a constant. So what I can do is I can take this 1 over x and I can factor it out of the limit. If you remember the limit properties from 1.3 in the book, there was one that said the limit of k times f of x is the same thing as k times the limit of f of x. So yes, x is a variable here, but since the function, the limit is in terms of h, this is a coefficient, okay? So moving that to the front, I have 1 over x times the limit as h approaches 0 of x over h times natural log of 1 plus h over x. Okay, now I'm going to use a variable substitution. This step is not necessary if you can kind of see what's going on with the log properties, but it is something that makes it easier for us to see what's happening. Okay, so what I'm going to do is I'm going to say and I'm just using another variable, so I'm going to say let a be equal to x over h. So I want a to be equal to this fraction that we have inside here. Okay, so when I do that, and then I put things in terms of a instead of h, we get, now the 1 over x I'm going to keep here, so 1 over x times the limit. Now, if h is approaching 0, let's think about what a does. So if h is approaching 0 and x is operating just as a constant, any constant divided by something approaching 0 is going to approach infinity. So I'm going to put this as a approaching infinity. Okay, and then this piece right here, the x over h, is the reciprocal of, is equal to a. So we have an a as a coefficient right here, and then we have times the natural log of 1 plus, and then h over x is the reciprocal of a. So this becomes 1 over a. Okay, so pause it, make sure that you understand what I just did. So what I'm trying to do is I'm trying to minimize the different variables we have in here, and I'm going to use a log property here in a second. So I want to make sure that that you're following what's happening, but we're putting it in terms of a so that it cleans up a little bit better for us. And as long as we're consistent and put everything in terms of a, then everything inside the limit, the 1 over x doesn't matter. But if we put everything inside the limit in terms of a, we still have an equivalent expression here. Okay. So the next step is to use a log property that says, I believe this is the power rule or something, the name doesn't matter, but it says that if we have a log, then if there's a coefficient in front of it, we can raise that to the expression inside the log, we can raise that to a power. Or you probably remember using this in the other direction, where if we have an exponent up here, we move that down as a coefficient. We're going to go the opposite direction. So we're going to write this as 1 over x times the limit as a approaches infinity of the natural log of 1 plus 1 over a raised to the a, because the a that was here comes up as an exponent. Okay, now next we're going to use a limit property, and the limit property allows us to move the limit inside the log function. Okay, and hang on, we're almost through this, so if you're feeling a little bit lost, just stick with me. Okay, so I'm going to write this as 1 over x times the natural log of the limit as a approaches infinity of 1 plus 1 over a raised to the a. Now, the reason I did this is because this expression right here is an important expression. This expression is the definition of something, which we're going to explore on the calculator here. Okay, so I'm obviously I can't plug in infinity, but I'm going to plug in a big number here into this expression. I'm going to do 1 plus 1 over that number raised to that number. So I'm going to write this as 1 plus 1 over, and I'm going to use 5 nines, okay, parentheses, raised to the 5 nines. 99,999, pretty big number. Okay? And then I'm going to do it again with a bigger number. 1 plus 1 over 1, 2, 3, 4, 5, 6. So 999,999 raised to the 6 of those again. Okay? And maybe this is starting to look a little familiar. Let's do one more. 1 plus 1 over, we'll do 9,999,999. Let me double check. Is that 7 of those? Yeah, okay. Raised to the 1, 2, 3, 4, 5, 6, 7. And we get, okay, so you may be thinking, hey, that number doesn't mean anything. Or you may be thinking, it appears that it's approaching about 2.71828 maybe. And this number might look a little bit familiar to us. Okay, and hopefully some of you at least are thinking, hey, I know what that number is. That number is E. Okay, so this is the limit definition for E, the base of the natural log. Okay, so I can replace this, everything in the brackets here, with an E. Okay, so because of the definition of E, we can say this is equal to 1 over x times the natural log of E, and natural log of E, hopefully we know what that is. That's equal to 1. So we get 1 over x times 1, which is 1 over x. Okay, so that was a lot of algebra and logs and limit stuff, but what we have done is we have determined that the derivative of the natural log of x is equal to 1 over x. Okay, so if we are looking for the derivative of natural log of x as a part of some other expression, it's just equal to 1 over x. Now here's something important. That does not mean that the natural log of something else inside here, like the natural log of 5x, is equal to 1 over 5x. This is only for having a single x on the inside. Natural log of 5x, we're going to have to use some log properties to simplify, okay? So I'm going to stop this video, and then the next one I'm going to do some examples using the log properties. If you need to go back and look at log properties, then go ahead and do that before you watch the next video.